But even more satisfactory for me was, if we have a theory of the nuclear force, if the proton is made out of quarks held together by this strange force that's weak at short distances and strong at large distances, we should be able to calculate anything we want about nuclei, and today we can. In particular, we can calculate your mass. Now, I'm sure you might have wondered sometime, what is the origin of your mass, of your weight? Now, of course, you might say it's the food I ate yesterday. So where does your mass come from? Well, you're made out of atoms that make up the molecules that they're made out of, right? So presumably your mass comes from the mass of the atom. But most of the mass of the atoms is in the nucleus. The electrons are very light particles. So what does the nuclear mass come from? Well, it comes from the mass of the proton and the neutron. Well, what does the mass of the proton come from? Well, the proton is made out of 3 quarks. So you might say, well, the mass of the proton comes from the mass of the quark. That's wrong. Quarks are very light. They're about as light as electrons. In fact, if they had no mass at all, they were massless, your weight would change only by, you'd only get a few % lighter. Not a good way to diet. So what is the mass of the proton come from? Well, you might, when you get on the scale in the morning and you see you gain some pounds or kilograms, you might be reassured to know that what you gained is energy. You're all made, your mass comes from the energy of the quarks and the quanta of the force that bind them, the so-called gluons. According to Einstein's famous equation, this is the only equation I'm going to write down, E equals mc squared. What that really means is that the mass of a particle is the total energy of that particle when its center of mass, when it's at rest. So proton at rest, its mass is equal to its total energy divided by c squared, c being the velocity of light. So what happens in QCD is that these very light quarks are rattling around inside the proton. They can't get too far out because then the force between them gets to be very strong. So they just roll around inside a region that's the radius of the proton, and their kinetic energy from their motion contributes to their total energy, and that's where your mass comes from. So that might make you feel better when you've gained a kilogram. You've gained a kilogram of energy. But it also means we can calculate what that mass is by calculating the energy of the quarks according to the forces that hold them together. And it requires dozens and dozens of people working for dozens of years actually on large computers to do the numerical calculations in this theory. We don't yet know how to do it with pencil and paper. It has to be done with large-scale computing, but it now can be done with incredible accuracy. And this is a list of some of the particles that were being discovered in Berkeley at the time, including the nucleons. This N is the proton or the neutron, so very close in mass. And these are the comparison of the measured numbers with the theoretical calculations, which have some theoretical errors, but they're quite small. We can now calculate your mass from first principles and the mass of all these particles. For me, that isn't a prediction. We knew what they were before, but it's what we call a postdiction. From first principles, with almost no parameters, we calculate the mass and the properties, the other properties, the scattering and so on of the elementary particles that we observe. Anyway, once nature has said, okay, your theory might be correct, at least it's not incorrect, the Swedish Academy sometimes regards that as important. And I'll give you a bit of Nobel Prize memories. So this is getting the Nobel Prize from the king. Actually, when you get the prize, you get three things. You get a medal, a gold medal, you get a certificate, which I'll show you, and you get a check. This is the certificate, which is really beautiful because they have Swedish artists where each laureate gets a separate original painting. You see here a depiction of three quarks inside a nucleus bound together by this force. And this is what it looks like in the theory. If you do the calculation, you try to pull the, remember a proton is made out of three quarks. You try to pull them out, you see again the flux is squeezed to these tubes, and it would take an infinite amount of energy to pull a quark out of the proton. And then after the ceremony, there's this incredible banquet. Now, according to Alfred Nobel's will, physics is number one, as it should. And so I got to sit next to the Queen. And this is the next queen, the Crown Princess, Victoria, who will be queen as soon as her father retires. And then during this banquet is quite spectacular, and I thought I would share with you a little of the banquet. So the banquet is held in the town hall of Stockholm. This is the middle of winter. It's very cold and dark. But the town hall is amazing room, which look has a room that's maybe 3-4 stories high. And this banquet goes on for 5-6 hours. Many courses and entertainment in between with 2,500 people. So I'm going to play for you a very short movie of the 24 hours of the banquet, squeezed down to 2 minutes. So it'll be very fast. Most of the time will be taken by the setting the tables, but you'll also see waiters delivering and some of the entertainment and some of the speeches very fast, and we might even have sound. Oops. Oh, that would be a pity if it doesn't work. How do I do that? So this is setting up. There are 500 waiters. are the guests coming in, the procession of the laureates. This is the waiting. Entertainment, opera. Okay. I hope someday you get a chance to experience this. It's quite a dinner. Anyway, the theory of the nuclear force was part of one of the completion in the end of the 20th century, 1970s, of a theory of matter and the forces that act on them. Not just the nuclear force, but the two other forces that act within the atom. And this is called sometimes the standard model of elementary particles. It could be called a theory. It is a list of the basic constituents of matter, up, down, quarks inside, neutrons and protons, the electron and its partner, the neutrino, the sisters of the leptons, muon and tau, and their neutrinos, and the strange and charmed top and bottom quarks. Altogether, 6 quarks, each of which has 3 colors and 6 leptons. And the more basic understanding of the 3 forces that act within the atom and the nucleus: electromagnetism, electricity and magnetism, the strong nuclear force, and the weak nuclear force. And one add-on that had to be put in to explain the properties of the weak nuclear force. The weak nuclear force is what's responsible for radioactivity. It turns one flavor of quark into another. And this is the standard model. Now, the standard model is a true theory of matter and force. And it's a fundamental theory because I can put the equation on a t-shirt. And from these equations, or from this expression, one can, following the rules of relativistic quantum mechanics, calculate just about everything we've ever measured in principle. If we do enough work, we can, as I showed you, calculate the mass of the proton, your mass. So it's a remarkably successful culmination of fundamental physics. We now have an incredibly successful theory of matter and force. It really should be called the standard theory of elementary particles. And since it was completed in the 70s, it has been tested the last 40 years with bigger and bigger accelerators, going to higher energies, shorter distances. There are very, very few deviations or phenomena that are not explained by the standard theory, at least in terrestrial experiments. But there are many hints that more is required. For example, astronomers have discovered that most of the matter in the universe is something they call dark matter because they can't see it. But since it has mass, particles have mass, they attract other particles gravitationally. And this dark matter affects the gravitational dynamics of planets and stars, and that's how it was discovered. And we now believe that most of the matter in the universe is in the form of dark matter. There's very little around us. So sitting in your chair, there are 500 dark matter particles passing through you every second. That's not very many. They're going about 500 kilometers a second right through you. And you don't feel them, luckily, otherwise they would call it cancer, because they interact very weakly with the kind of matter that makes up the standard theory. But for that reason, it's very hard to detect them, and they're very massive, so it's hard to produce them. We still haven't managed to figure out what they are. That's one of the biggest challenges we face at these big accelerators or detectors underground. And there are many other clues, including the fact that if we take our knowledge of the standard theory and interpolate it to even shorter distances, we might ask, after all, the proton is made out of quarks. What are quarks made out of? Subquarks. Will it just keep going on forever? Matter is made of molecules, molecules are made of atoms, atoms are made of nuclei, nuclei are made of quarks, quarks are made of, well, we don't know. But if we extrapolate our theory, experimentally, we can only go to distances which are here, 10 to the minus 17, by now 18, that's a millionth of a millionth of a millionth of a centimeter. Much smaller than the nanoscale. This is the nano scale. But theoretically, a theorist can extrapolate forever. And when this was done, when the theory was completed, it seemed to indicate that the strong force, which gets weaker when you extrapolate the shorter distance, higher energy, the electromagnetic force, which gets stronger, and the weak force unify, come together as if there's a unified force. If you do experiments, you will see this very directly at very short distances. And for the last 40 years, many of us have been exploring that possibility. Unification of all the forces, including the fourth force of nature, which was the one that was first understood by Mr. Newton, called gravity. Now, when theorists do this kind of extrapolation, what does it tell you? And they discover, well, it looks like the forces all come together in unity. Some of us regard that as a very important clue for the unification of all the forces together, including gravity, at very, very, very short distance. Very high energy. Way beyond what we can measure directly today. But it might be just a coincidence. So lesson number 8. And I'm not sure how to tell you this lesson. It is crucial in doing and exploring, whether it's climbing up a mountain or exploration in science, in physics, any science when you're exploring new territory, to trust, to develop your intuition. You have to make a decision as a scientist. Is this an important clue, which I'm going to spend 30 years of my life pursuing, or is it a coincidence? And we don't know the answer. And just this extrapolation might tell you that the forces unify, but it doesn't tell you how they unify. And since we can't do experiments up here, it makes life very difficult, but we have no choice but to try. There are some fascinating ideas, however, that say that there will be something very new and revolutionary in our understanding of space and time already down here. Exactly where the LHC, the big accelerator at CERN, the Large Hadron Collider, is now doing experiments. This is a picture of the ring, which is 20 kilometers around, that runs between France and Switzerland. To give you some idea of perspective, this is the Geneva airport here. This is the size of the accelerator. Much bigger than that one in Berkeley. In this ring, protons are accelerated. They travel at 99.999995% of the speed of light in both directions, two beams. So they go around millions of times from France to Switzerland, no border control, and at three different